When talking about the moons in our solar system, many people immediately think of our own moon or the icy satellites of Jupiter. But there's one world that scientists have long regarded as a prebiotic laboratory, a place with a thick atmosphere and stable liquids on its surface, much like our Earth, but at freezing temperatures. That world is Titan, the largest moon of Saturn. Titan, also known as Saturn VI, is the only known moon with a significantly developed atmosphere, composed of more than just gases. It's the second largest moon in the solar system, surpassed only by Jupiter's Ganymede. In fact, in terms of diameter, Titan is even larger than the smallest planet, Mercury, though its mass is only about half as much. The existence of Titan was discovered by Dutch astronomer Christian Huygens on March 25, 1655. Inspired by Galileo's discovery of Jupiter's major moons, Huygens improved his telescope design, which led to his finding of this moon. At first, he simply called it Saturni Luna. It wasn't until 1847 that John Herschel officially named it Titan, after the Titans of Greek mythology, the brothers and sisters of Cronus. Titan orbits Saturn with a period of 15 days and 22 hours. Like Earth's moon, Titan is tidally locked, meaning its rotation period is synchronized with its orbital period. Titan also has zero axial tilt, meaning its rotational axis is perpendicular to its orbital plane. Titan is composed mainly of water ice and rocky material. Based on its average density of 1.88 grams per cubic centimeter, scientists estimate that it consists of roughly half water ice and half rock. Its internal structure is likely layered, with a rocky core about 3,400 kilometers in radius, surrounded by layers of crystalline ice. The most fascinating aspect, however, is evidence from the Cassini spacecraft suggesting the existence of a subsurface liquid ocean beneath Titan's icy crust. This liquid layer is believed to be a mixture of water and ammonia, located between the outer ice shell and the deeper layers of high-pressure ice. This evidence is supported by Cassini's detection of natural, extremely low-frequency radio waves in Titan's atmosphere, which are thought to reflect off the ice-liquid boundary of the underground ocean. Furthermore, variations in Titan's gravitational field as it orbits Saturn also support the existence of a liquid layer beneath the surface and suggest that the outer icy crust may be decoupled from the solid core. Before the Voyager 1 spacecraft's flyby in 1980, Titan's size had been significantly overestimated, as its thick atmosphere extends miles above the surface, increasing its apparent diameter. This atmosphere is so dense that it blocks most visible sunlight, making surface features extremely difficult to observe. Titan's atmosphere is unique among all moons in the solar system. It is even denser than Earth's, with surface pressure about 1.5 times greater. Its composition is 98.4% nitrogen, making Titan the only celestial body besides Earth with a dense, nitrogen-rich atmosphere. The remaining 1.6% consists mostly of methane, along with traces of hydrocarbons and other complex compounds. The orange hue observed from space is caused by small amounts of complex chemical compounds, possibly tholins, tar-like organic precipitates. Tholins form when ultraviolet sunlight breaks down methane in Titan's upper atmosphere, creating a thick haze that completely obscures the surface. The atmosphere is so dense and Titan's gravity so weak that scientists have calculated a human could actually fly through it by flapping wings attached to their arms. However, methane in Titan's atmosphere is gradually converted into hydrocarbons by solar radiation within about 50 million years, a short time compared to the solar system's age. This raises a profound question: what replenishes Titan's methane supply? Scientists believe the answer lies in Titan's internal geological activity. The detection of argon-40 in the atmosphere suggests that cryovolcanoes have erupted plumes of lava made of water and ammonia. The cryovolcanism theory is now considered the primary source replenishing atmospheric methane that sunlight continuously breaks down. The pressure required for these icy volcanic eruptions may come from frozen water layers pressing down on a subsurface layer of liquid ammonium sulfate, triggering large-scale outbursts. Titan's surface is described as complex, shaped by liquids, and geologically young. Thanks to the Cassini spacecraft, which used radar altimetry and synthetic aperture radar, scientists were able to peer through Titan's dense haze and map its surface in detail. The most striking discovery is the clear evidence of stable liquids on the surface, making Titan the only known celestial body besides Earth to have this feature. However, these liquids are not water, but hydrocarbons such as liquid methane and ethane. Although Cassini initially failed to detect sunlight reflections from liquid surfaces when it arrived in 2004, radar images taken later at high northern latitudes revealed large, flat, and dark patches near the poles. In January 2007, scientists announced definitive evidence of lakes filled with methane. Several large lakes have been identified in the northern hemisphere, most notably Kraken Mare, a vast liquid body. In the south, a dark feature called Ontario Lacus was also confirmed to be a lake. In June 2008, Cassini's infrared instruments confirmed the presence of liquid ethane at Ontario Lacus. Titan's surface also displays vast, bright and dark regions. Xanadu is a large, reflective equatorial area, roughly the size of Australia, crisscrossed by valleys and canyons. These features may be channels carved by flowing liquids, suggesting that ancient fluvial systems once eroded the terrain. In addition to lakes, Cassini's radar images reveal dark equatorial regions that are extensive plains covered with longitudinal dune fields. The sand on Titan is thought to be made of icy grains eroded by methane rain, or solid organic materials produced by photochemical reactions in the atmosphere. These dunes mostly stretch from west to east, shaped by a combination of steady zonal winds and variable tidal winds, winds that are over 400 times stronger than the tidal forces the Moon exerts on Earth. Titan's surface has very few impact craters, indicating that it is geologically young. Many craters appear to have been filled in by hydrocarbon rain or materials ejected from cryovolcanic activity. Titan's thick atmosphere also acts as a protective shield, reducing the number of meteor impacts by roughly half. Titan's surface temperature is extremely cold, about 94 Kelvin, or negative 179 degrees Celsius. At such a temperature, water ice does not sublimate, which means the atmosphere contains virtually no water vapor. Titan's atmosphere produces two opposing thermal effects. Its haze causes an anti-greenhouse effect by reflecting sunlight, cooling the surface far more than the layers above, while methane contributes a greenhouse effect that helps warm the surface. Just as Earth has a hydrological cycle, Titan is governed by a methane cycle. The Huygens probe discovered that Titan's atmosphere periodically generates rainfall composed of liquid methane and other organic compounds. Titan's climate includes winds and rainfall-driven surface features similar to those on Earth, such as dunes. Atmospheric circulation models show that the winds blow eastward following Titan's rotation, and that Titan is a super rotator. Its atmosphere spins faster than its surface. The wind patterns on Titan are dominated by a single, large Hadley circulation cell. This system transports methane clouds from one pole to the other, effectively giving Titan a tropical-style climate, though one that exists at freezing temperatures. Scientists have observed pronounced seasonal differences, especially near the poles. In September 2006, Cassini captured an image of a massive cloud about 2,400 kilometers in diameter above Titan's North Pole, containing methane, ethane, and other organic compounds. This cloud is believed to have been raining or even snowing over the North Pole. Since one Titan year equals about 30 Earth years, the unequal distribution of methane lakes, more in the northern hemisphere than in the southern one, supports the hypothesis that methane rain occurs at the poles during winter and evaporates during summer. Much of humanity's curiosity about Titan was satisfied thanks to the Cassini-Huygens mission, a joint project between ESA and NASA. After Cassini arrived at Saturn in 2004 and began mapping Titan's surface with radar, the Huygens probe successfully landed on Titan on January 14, 2005, making it the farthest celestial body from Earth on which a spacecraft has ever landed. The Huygens landing site was located just outside a bright region known as Adiri. The probe captured images of gray hills composed mainly of water ice, and after landing, it photographed a dark plain scattered with small stones and pebbles, also made of water ice. Importantly, Huygens observed signs of erosion at the base of some rocks, suggesting possible fluvial activity in Titan's past. With its dense nitrogen atmosphere and the presence of surface liquids, Titan is considered a possible analog to the early Earth, but at far lower temperatures. Scientists regard Titan as an ideal laboratory for studying the chemical processes that could lead to the emergence of life. Simulation experiments have shown that, in an atmosphere like Titan's, exposure to ultraviolet radiation can produce complex organic molecules, such as tholins. These compounds may form through the breakdown of nitrogen and methane, creating hydrogen cyanide and acetylene as intermediates. But has life actually formed there? Titan lacks stable liquid water on its surface, yet scientists remain optimistic that liquid water may persist beneath the outer icy crust, either temporarily from meteor impacts or within a subsurface layer of liquid water ammonia mixture. Life might exist in these extreme underground environments. Another intriguing hypothesis proposes methanogenic life organisms that could use methane as a solvent and hydrogen as an energy source, surviving directly on Titan's frigid surface. A particularly exciting future project is Dragonfly, a NASA mission under the New Frontiers program. Dragonfly is a rotorcraft drone designed to fly between multiple locations on Titan to study its organic chemistry, geology, and atmosphere. Scheduled for launch in 2028 and arrival in 2034, this mission aims to search for prebiotic compounds and explore Titan's methane-rich surface in unprecedented detail. Titan is a true treasure of the solar system, hidden beneath its thick orange haze. It's a one-of-a-kind world with a nitrogen-rich atmosphere, vast seas and lakes of liquid hydrocarbons, and clear evidence of a methane-based climate cycle. Despite its freezing temperatures, Titan offers us a rare glimpse into the prebiotic chemical conditions that may have once led to life on Earth. Bold missions like Dragonfly promise to unravel its remaining mysteries and search for complex organic compounds. Titan is like a cosmic safe, locking away the secrets of life's origins, and humanity is slowly unlocking it step by step. What do you think awaits us beneath Titan's mysterious haze? Share your thoughts in the comments, and don't forget to subscribe. See you on our next journey through the cosmos.